So in this, can you go to the next slide, Josep? So in this presentation, I will start talking about a bit about what we do in the work package of co-design, profiling, and performance analysis inside the exaFOAM project, just to put you in context about what we are presenting. And then I'll explain what is the performance analysis methodology and tools that we use in this project, so that you will be able to understand better everything that Josep will explain later, because he's going to present a performance analysis of an OpenFOAM use case. And we will end with explaining a bit which will be the next steps that we will be doing in this work package, in this project. So next, in the work package 5, that it's about co-design, profiling, and performance analysis, we say that we do, we start saying that we do co-design, because what we try to do is to keep the co-design wheel rotating or moving. So we try to analyze some of the use cases of the project, and based on this analysis, we get some information. This what we call co-design insight. This information can be directed to the application developers on ways to improve their code, but we can also get information for computer architects on which are the issues of the hardware that we are facing, or to other components of the system software. Could be programming models, compilers, libraries, the different layers of the software stack. With this information that we give to one of these partners, if we give that information to application developers, they can implement the changes or the suggestions that we make them in the code. That code then is deployed, validated again, and we can start again doing the performance analysis and understanding which are the next bottlenecks that we are facing. This is the general overview of how we fit inside the project. And then now let me explain a bit the methodology that we follow for this performance analysis. So next, please, Josep. The methodology that we follow has different steps. We start trying to identify the structure of the code that we are analyzing. We select the focus of analysis. The focus of analysis is the part that we will focus on analyzing. It can be the whole execution, it can be a time step, or it can be a part of the time step, depending on what we are interested in. From this focus of analysis, this part of the code that we want to analyze, we get some efficiency metrics. I'll explain later which are these efficiency metrics, but they are depicted in this picture. They are different based on which one of these metrics is low. It tells us where to look. From there, we do the detailed analysis, and from the detailed analysis, we can gather some conclusions and suggestions. This is quite abstract, but it's nice that you see here the theory, because then Josep will explain this performance analysis, and you will see each one of these steps explained by him and applied to a real analysis of a use case. So next, please. For this, we use different tools. The first thing that we need to do is to get a trace. The traces are the fundamental thing with what we work for doing our performance analysis, and the tracings are capturing what is happening inside a real execution. So we start from a binary and an input, and without modifying the binary or the code or recompiling or anything, we run with using an LD preload and the library. With this LD preload, the library is able to intercept the MPI calls and to generate the PRB file, which is a Paraver trace. Here in this trace, we have all the information of what happened during this execution, time-stamped, so that we can then rebuild what happened in the execution. So next, please. From this trace, one of the first things that we can do is we use a tool that we call the basic analysis. And this tool provides us some kind of table like the one that you are seeing below. This table has the different efficiency metrics that we have defined in our methodology. These efficiency metrics tell us where to look. Next. And with this, we know can open the Paraver trace file with Paraver, which is a visualizer of the traces. And with Paraver, we can analyze in detail what's going on inside the execution. Paraver has different views. One kind of view is the timeline. The timeline is this kind of windows that you are seeing here at the bottom, or we can also see histograms. This allows us to get a very detailed performance analysis of these trace that we obtain. Let me explain a bit more in detail the different views, because then you will see a lot of these windows and the screenshots in Josep's presentation, so that you are used to that. So next, please. So the efficiency model that we use, this is a set of metrics. It's hierarchical and it's multiplicative. This means that the product of the childs give the value of the parent metric. These are efficiency metrics. This means that it's telling us how much efficiency in terms of CPU time we are losing due to one of the metrics. So for example, if the parallel efficiency in this case is 72%, this means that 18% of the CPU time that this execution wasted, it was due to the parallel efficiency. The bottom metrics, the ones that are ended with scalability, are computed based on a base case. We cannot compute them based on its own trace, because we don't know the optimum value of each one of the metrics. So we don't know which is the optimum value of the IPC, of the number of instructions executed, or the frequency. So we always base it on the first column. Each column in this table corresponds to a different execution. So you can get one of these tables just with one column when you only have one trace, but we can obtain several traces to study how these efficiency metrics change when we scale this application. And when we get this kind of table, we can we look at values that are very low. Below 80% is really already worth looking at. And also trends. So if we see values that are not very low, but they trend to go down, for example, in this case, you could see the instruction scalability is slowly going down, but it means that at the end, that metric will be a bottleneck when you keep scaling. And also in some cases, two values going up. So in this example that we have here, for example, the IPC scalability, which is a value that it's going up. Even though it's going up, it can be a problem, because it can be that it can hide another problem. And it also means that the values for the first column were not optimal. So we were able to obtain a much higher value of IPC when running with more processes. Maybe there's something that can be solved also. So next, please. When we analyze with Paraver, as I said, we have different kind of views. The ones on the left-hand side of this image are timelines. Timelines represent part of the execution. In the x-axis, we have the time, and in the y-axis, we see the different objects. In this case, are MPI processes, because this is an MPI-only application. But if you have a hybrid application, you would see the MPI processes and the threads. So each line of one of these views is one MPI process, and the color can change from view to view. You can select with Paraver what do you want to see. In the timelines, you have two coloring schemes. In the top one, you are seeing one that is a gradient mode, where you go from green for low values to blue for high values. And in the bottom one, you have an example of a code color. In this case, we have absolute values where one value corresponds to one color. In this case, we're seeing MPI calls and they are coded. So if we know that yellow is an all reduce, then we can see that when the all reduces are happening. On the right-hand side, we see histograms. Histograms are another way of analyzing the data in the trace. where the data is aggregated. So we don't have anymore the timestamp information, but we have the aggregated values. In the top one, the histogram have in the x-axis the control scale, and in the y-axis we still have the different MPI processes. And then you can select which is the control scale, so what do you see in the x-axis, and also which is the color, which is the metric representing the color. In this case, for example, it's the duration of the different MPI calls. This information, you can see it in a graphical mode, like in the top one, or you can see it in the numerical way. That's what we're seeing in the bottom one. In the bottom one, each column corresponds to one MPI call. Each row corresponds to an MPI task. And then inside each cell, we see the percentage of time that we spent inside that MPI call. All this is configurable from within Paraver, and you can get these different kind of views. And now, next, Josep will present you an example of using this methodology when analyzing one use case of OpenFOAM.
Okay, thank you. Yeah, I will present one analysis that we are doing right now on the case of driver of one variant of driver case, that it's a variant with open close cooling and with rotating mesh. Basically, for my understanding, it's a car with rotating wheels. So in this case, for the execution, we used Mare Nostrum 4, that it's a supercomputer that we have here in BSC in Barcelona, Spain. And well, this is a configuration of the nodes. And for the case, we used OpenFOAM version 21.06. And here is the compiler that we use GCC and OpenMPI for MPI. And well, okay, for the, as Marta said, we first did the focus of analysis, and for the execution, we used input of 250 million cells, sorry, and we used PimpleFOAM solver. So first of all, what we did was execute the case with only 3 time steps, and we open it the trace with 2 different views. The first one, the top one is the useful duration, and the bottom one is the MPI calls. We see in these views that the time steps are very differentiated, and there is an initialization phase also. And as Marta said, the colors, and here is the legend for the colors with the gradient scale, and in the bottom one, the colors represent the different MPI calls, but it's not gradient, it's a color for every MPI call. So for the focus of analysis, we did the analysis for only 1 time step. And here we use the tool model factors. That is the tool that Marta called analysis. I don't know how it called, but it's
basic analysis.
Yeah, basic analysis, sorry. We did the basic analysis of 1 time step, and here are the results where we executed the case for different amount of ranks, and we saw how the metrics behave in every execution, and we saw the problematic metrics was the load balance, because there is a trend that it's going down, like Marta said, that it's a trend, this, and yeah. And in the communication, we saw also that the serialization was very bad, because as you see, the colors that are very reduced, and also the instruction scalability started good, but starting from 768 ranks, it was downgrading very fast. And well, also we saw that the IPC was scaling up, so there was a problem with the first execution with 96 ranks. Okay, so here we have one time step, the two views that we saw before, the one with useful duration and one with MPI calls. But these MPI calls, now only we are filtering the calls only to show the collective communications. Why we do that? Why we do that? Because in the sometimes with sometimes what we want to see is differentiate some different parts on the execution. And as you can see in this view of the useful duration, is not showing easily the different parts of the time step. And with only with the MPI collective communications, we were able to see that there were two different parts. The first one, a part that it's only done once, and the part two that it's repeated in this time step, it's repeated 10 times. So for the analysis, we did the here we enter a little deeper in the focus of analysis, and we divided the model factors for we did the model factors for the two different parts. The part one, we saw that there are more values in red, and in part two there are also bad, but are not as bad as part two. And going, let me highlight the problems here. Sorry, and here at the top we see the four metrics that we saw in one time step. It's like a summary that we saw before. And in the part one, we see that the load balance and the serialization are very bad. And in the part two, the load balance and serialization are also bad, but the problematic ones are in the part two. And in the instruction scalability, the two of the parts are the problematic ones, because we see that when they reach 768 ranks, it starts to go down, the metric. And so we started the analysis for the load balance in the part one. Here we see that assume only focusing on the part one, where we see that this part is divided in different regions. We were able to identify 5 different regions, where here we analyzing the load balance, we saw that the first region and the last region had a good load balance. So we focused in the 3 middle ones, the region 2, 3, and 4. And here is a zoom for every of the three regions, and we see that there is a different load balance in the different regions. it's a different pattern, but it's a load balance in all of the three regions. Sorry. Here we can see that some ranks are executing code alone because the black part is not executing anything. In the region 3, we can see that there is some I don't know how to call it, but there are very load balance in every little iteration. And in the fourth region, we see that there are so little execution steps, but there are some parts bluest than others. So this also happens to be a load imbalance. So for these three regions, we started to try to correlate the load imbalance with instruction imbalance. So what we did here, for every region, we got the one histogram where we can see in the horizontal axis, we can see the time execution bursts or durations, and in the vertical axis we can see the ranks. So the dots that are in the left side are more execution are ranks that are executing more time, more duration in only one burst, and the left ones are the ranks that are executing less time, only one burst. So the colors represent the also going from green to blue. It's a gradient representation of the amount of instructions that they execute. So the more bluest, the more executions of the instructions, the more instruction executed. So how do we correlate the load imbalance with the instruction imbalance? Because we see that, like in the second region, that it's the first view that we have seen, we see that as the execution is, as the dots are in the right, they are more bluest, and as they are in the left, they are more greener. So here we can correlate the load imbalance with the instruction imbalance, and in the middle one, in the region, we also can correlate it because we see that the same pattern here, that the left are greener and the right side are bluest, but in this last region, the right one, we cannot correlate the load imbalance with the instruction imbalance. So this is a summary that these two regions are the load imbalance of these two regions are caused by instruction imbalance, and this other region we have still to investigate it. And if we and we wanted to go deeper in the study of the region 2, where we saw these ranks that were executing something, and they were alone because they are not, this is not parallelized nothing. And what we see here with a zoom, with different zooms, we saw that before the long computation, the bluest ones, there is a point-to-point communication only to them. So then, with the help of Extrae, we with the help of Extrae, we can instrument the code to see where the problematic region or part of the code is happening. So it's as easy to put some events in the functions to try to see where the problem is. So here you put it some custom events like 100 and 200, and when open it with Paraver, the view, it paints us the colors of the event. Sorry, it paints us the events with a different colors. So with that, we can go to the developers and say what is the problem, and be able more easily to correct it or to identify and so on. And okay, with that, we saw that here I am in the previous slide. Here I am showing that we found the load imbalance of the part one that was caused by three different regions, and also the serialization efficiency, because it was hidden in this part, that this is it's I don't know how to say it, but it's load imbalance, but hidden as a serialization efficiency. So we can say that we also found this problem, and now we are going we are going to analyze the instruction scalability problem. So in this part, in this metric, we got the different regions and put them in a and count the different amount of executions of instructions executed, sorry, and in the different amount of ranks, and we saw that the problematic regions was the region 2 and region 4. But we saw different patterns here, because in the region 2, the number of instructions changed with the number of MPR ranks, and in the region 4, the number of instructions increased with the number of MPI ranks. So this is we saw also the problem with the instruction scalability, that is because of these two regions. And that's all for the analysis that we've done so far. So here is a summary that first we analyzed one time step and divided it in two parts. In the part one, we identified the load imbalance that was caused by two of the regions, and the serialization also by one of the regions of the load imbalance, and the instruction scalability also we found it. And the next steps will be analyze the part two, and that's all for my analysis. Now, Marta, if you want.
Thank you, Josep. So just to wrap up, we tried to explain our performance analysis methodology and tools, and showcase that applied to an OpenFOAM use case. So probably some of the questions that arise from this presentation are, which part of the code is this and that, because Josep keeps telling it the time step, the part one, part two, and then the different regions within that. And that's the where we don't have yet the information on which part of exactly of the code is that, which to start the performance audit, I think it's the correct starting point. So we start from the point of view of not knowing anything about the code. So we are not biased by that. I think that's the way to go. But at some point after the analysis, it's very important to know where is that. So to get that, and without having to go by hand, as Josep was showing in some of the cases, to locate the code, we added some calls to the API of Extrae to be able to locate that exactly part of the code that was causing that problem. But the next steps would be nice to add this extra instrumentation inside OpenFOAM. So in some places that we already know that can be interesting to have monitored, so that for next analysis we are able to already know to which part of the trace corresponds to the code that corresponds each part of the trace. So those are the next steps. We will keep doing analysis for the OpenFOAM, different OpenFOAM use cases that we have in the project, but we will also try to do this integration, so to be able, when we have our analysis, be able to pin exactly to which part of the code we are referring when we find an issue. And that's all from our side. We will be happy to answer any questions that you have.
So, thank you, Marta. Thank you, Joseph, for the very interesting presentation. And I want only to stress here that Extrae and Paraver, they are open source. You can download them from the BSc website, and it works with OpenFOAM without recompiling it with debug flags. So it can work better if you have debug flags. You can see more information. Correct me if I'm wrong, so Marta, but you can run Extrae and get these traces with the normal compilation, with our production compilation of OpenFOAM.
Exactly. So that's the idea. So from without compiling, you get the traces. Then what I was saying, you can add the API, then you need to recompile. But without doing anything, you already can get this and information on how your execution is performing.
And which, so from my personal experience, is very nice. It's you can get a lot of insight with this very detailed traces analysis that you can do with Paraver, but also only with the pop metrics that you can get automatically running this script. I don't remember the name of the script now. It's
Basic analysis or model
basic
functions.
analysis, yeah, basic analysis. And I can only tell to the participants that if you're really interested in performance analysis of OpenFOAM, these are very nice tools to start with.
Thank you, Flavio.
Okay,
Thank you.
and